Salicylates overview. History of salicylates. Aspirin, the miracle drug, actually is one type of salicylates. Historically, anti-inflammatory effects of the aspirin was discovered from the leaves of willow tree. Beginning in Mesopotamia, Assyrians in Iraqi Sumer have written in clay stone information about using these leaves for rheumatic inflammation and diseases, while in Old Egypt the leaves have been used after decoction and extracting the liquid for joint inflammation. Even Hippocrates have described using these leaves for fever, inflammation, and delivery pain. The anti-inflammatory effects is due to the presence of salicylic acid moiety in these plants. At the end of the 17th century, salicine, which is a glucoside, was extracted from willow. Salicine was later used to produce salicylic acid and then checked for treatment of rheumatic fever and joint disease, but it caused stomach irritation and had a bitter taste, so it has not been widely used. Scientists later thought of a chemical modification, which is acetylation. So now we have the structure called acetyl salicylic acid or aspirin. In fact, aspirin is derived from two words, A for acetyl and spirin for spireulmarine, which is the scientific name for meadowsweet, the natural original source for chemical structure of salicylic acid in 2D and 3D. The salicylic acid moiety has 7 carbon atoms. 6 of them belong to the aromatic ring, while 1 belongs to the carboxylic acid moiety. Physicochemical properties of salicylic acid. Salicylic acid molecular weight is 138.12 gram per mole, and it is present as white crystals or crystalline powder. It is odorless and stable in air but may discolor in sunlight. The structure is orthohydroxybenzoic acid or 2-hydroxybenzoic acid, which means that the hydroxyl group is in position ortho to the carboxyl ring of benzoic acid. It is aromatic and acidic. Its melting point is 158 centigrade or Celsius, and boiling point is 211 Celsius. It is sparingly soluble in water. 1 gram of salicylic acid is soluble in 460 milliliters of water, but it is soluble in organic solvents and very soluble in ethanol. This is because only 2 polar groups are present, while the benzene moiety is non-polar. Acidity of salicylic acid. pKa1 comes from the carboxylic acid moiety, while the other pKa comes from the phenolic OH moiety. Carboxylic acid moiety is more acidic and thus contributes more to the acidity of salicylic acid than the phenolic moiety. This is because of resonance and electronegativity factors.
Preparation and mechanisms of preparation of salicylic acid. Kolbe-Schmitt reaction. The Kolbe-Schmitt reaction, or Kolbe process, named after Hermann Kolbe and Rudolf Schmitt, is a carboxylation chemical reaction that proceeds by heating sodium phenoxide, the sodium salt of phenol, with carbon dioxide under pressure, then treating the product with sulfuric acid. The final product is an aromatic hydroxy acid, which is also known as salicylic acid, the precursor of aspirin. Reaction mechanism. The Kolbe-Schmitt reaction proceeds via the nucleophile addition of a phenoxide, classically sodium phenoxide, to carbon dioxide to give the salicylate. The final step is reaction of the salicylate with acid to form the desired salicylic acid. Alkaline hydrolysis of ester. Salicylic acid is prepared from methyl salicylate by hydrolysis of ester group with aqueous alkali, example, sodium hydroxide or potassium hydroxide. Salicylic acid is a monohydroxy benzoic acid, a type of phenolic acid and a beta-hydroxy acid. This colorless crystalline organic acid is widely used in organic synthesis and functions as a plant hormone. It is derived from the metabolism of salicine. The mechanism. Number 1. Nucleophilic addition of OH ion to the carbonyl group. Number 2. Proton transfer to an ionic form of tetrahedral intermediate. Number 3. Dissociation of tetrahedral intermediate. Number 4. Proton transfer yields an alcohol and carboxylate anion.
Reaction of salicylic acid. The Reimer-Tiemer reaction of salicylic acid with the chloroform and alkali in equation 1 result in the 3 and 5 formyl derivatives. If the reaction is carried out with carbon tetrachloride, the corresponding dicarboxylic acid form equation 2. The products 2 and 3 are 2-hydroxy 1,3-benz dicarboxylic acid and 4-hydroxy 1,3-benz dicarboxylic acid. Chloromethylation. Alkylation involving formaldehyde in the presence of hydrogen chloride is known as chloromethylation in equation 3. The reagent may be a mixture of formalin and hydrochloric acid, paraformaldehyde and hydrochloric acid, a chloromethyl ether, or a formal zinc chloride is commonly employed as a catalyst, although many other Lewis acids can be used. The final product is 5-chloromethyl salicylic acid. Condensation. The reaction of salicylic acid with formaldehyde in the presence of catalytic amount of strong mineral acid results in the condensation product methylene 5,5-disalicylic acid. Nitration reaction of salicylic acid. Mechanism of nitration involves electrical field generation, attack on the benzene ring by acetyl nitrates, by placing a nitro group on the aromatic ring system via aromatic substitution reaction. Here calcium nitrate is used as nitratic agent in the presence of acetic acid. Two groups of CO2H and OH in the salicylic acid complement each other since they both direct entering nitro group to the 5th position and the 3rd position and both electronically favored. The nitro group is attached in the 5th position and not the 3rd position. We can also use anhydrous nitric acid or concentrated sulfuric acid as a nitrating agent.
Now let's take some examples of salicylate. Most of the salicylic acid drugs, commonly referred to salicylate, are either marketed as salt of salicylic acid such as sodium, magnesium, triethanolamine salicylate, or as ester derivatives such as aspirin, or amide derivatives such as salicylamide, or combination of two molecules of salicylic acid called salicylic acid or salicylate. Now we will briefly explain each of them, starting with the salicylate. Salicylate or salicylic acid is a dimeric benzoate ester form obtained by intermolecular condensation between the carboxyl group of one molecule of salicylic acid and phenol group of other.
Physicochemical properties of salicylate. Salicylate is a white crystalline powder. It has a molecular weight about 258.23 gram per mole. It has a melting point 147 centigrade. It's aromatic due to contain benzene ring and acidic due to contain carboxyl group. Salicylate has a pKa 9.8 for aromatic ring and 3.5 for carboxyl group. It is very slightly soluble in water, but soluble in organic solvent such as chloroform, ether, and others. Chemical structure of diflunisal. Diflunisal is organofluorine compound. It's longer acting and more potent drug than aspirin due to it has a contain two fluorine group attached 5 position of salicylic acid, and that make it more lipophilicity. Physicochemical properties of diflunisal. Diflunisal has a molecular weight about 258.23 gram per mole. It has a melting point about 210 centigrade. It's also aromatic and it's also acidic. Chemical structure of methyl salicylate. Methyl salicylate is a flavoring agent found in oil of wintergreen, which is a sweet smelling member of the aspirin family. Physicochemical properties of methyl salicylate. Methyl salicylate has a molecular weight about 258.23 gram per mole. Has a melting point about minus 8.6 centigrade and boiling point about 223 centigrade. It's also called methyl 2-hydroxybenzoate. It's contain methyl group, and this methyl group gives more lipophilicity. It's aromatic and acidic like salicylate, and also like salicylate is slightly soluble in water, but more soluble in organic solvent. Methyl salicylate is yellow or reddish color liquid, sometimes colorless, and has a minty coal odor. This characteristic odor for methyl salicylate. Chemical structure of salicylamide. Salicylamide is a derivative of salicylic acid that is fairly stable to heat, light, and moisture. Salicylamide contain amide group and also phenol group. Physicochemical properties of salicylamide.
Salicylamide has a molecular weight about 137.14 gram per mole. It has a melting point about 140 centigrade and a boiling point about 181.5 centigrade. It's aromatic and it's also acidic. Salicylamide is the common name for orthohydroxybenzamide. It is slightly soluble in water and soluble in organic solvent. It appears as white or slightly pink crystals with a bitter taste and leaves a sensation of warmth on the tongue. Chemical structure of acetyl salicylic acid, or called aspirin. Aspirin, an ester of salicylic acid, or acetylation of salicylic acid. It's called acetyl salicylic acid. Was introduced into medicine in 1899. Aspirin composed of three groups: carboxyl group, and acetyl group, and benzene ring. Physicochemical properties of aspirin. Aspirin it appears as white crystal or crystalline powder with a bitter taste. It has a molecular weight about 180.158 gram per mole. Aspirin is odorless, but in moisture it is gradually hydrolyzed and acquires odor of acetic acid.
Acetic acid molecule detach itself from it, thus required to protect aspirin and acetic acid are formed. Synthesis of aspirin from benzene. First, benzene is alkylated to cumin isopropyl benzene by Friedel-Crafts reaction. Oxidation by air gives cumin hyperperoxide, which is often hydrolyzed to phenol by treatment with aqueous acid. Salicylic acid is obtained by orthocarboxylation with carbon dioxide in Kolbe-Schmitt reaction. Lastly, Acylation with acetic anhydride affords acetyl salicylic acid. Mechanism of aspirin synthesis from benzene. Benzene undergoes Friedel-Crafts alkylation with the propylene. Yield of this step is a cumin isopropyl benzene. The second step of the mechanism is oxidation by oxygen from atmosphere to produce cumin hydroperoxide. In the third step, phenol is produced. Phenol is obtained by decomposing the cumin hydroperoxide in the presence of dilute aqueous acid. The mechanism for this transformation begins with protonation of the hydroperoxide. This allows expulsion of water molecule with the rearrangement to an isopropyl carbocation ether. Attack of water molecule at this carbocation center is followed by decomposition to the products of acetone and phenol. Kolbe-Schmitt reaction. In this step, phenol is orthocarboxylated to salicylic acid. This is accomplished by Kolbe-Schmitt reaction using strong base and carbon dioxide gas. Treatment of phenol with sodium hydroxide generates an electron-rich sodium phenolate. This species reacts as an enolate nucleophile, doing a nucleophilic attack on the carbon dioxide. The orthoregiochemistry is favored over para by coordination of the incoming CO2 by the sodium cation. An acidic workup protonates the carboxylic acids and allow tautomerization to restore aromaticity. The final step of aspirin synthesis is acetylation of the salicylic with acetic anhydride. Salicylic acid is reacted with one equivalent of net acetic anhydride in the presence of zinc oxide. The zinc oxide catalyzes acetylation by coordinating of the carbonyl oxygen of acetic anhydride, increasing the electrophilicity. Thus, a nucleophilic attack at this carbon center by the phenol of salicylic acid is promoted. Zinc oxide also acts as the base in this reaction, giving zinc acetate as byproduct.
Chemical reactions of aspirin. Aspirin, also known as acetyl salicylic acid, has an ester functional group. Just like esters, aspirin can undergo hydrolysis under acidic and basic conditions. So, the basic hydrolysis of aspirin. Aspirin will react with a base, just like NaOH, to produce salicylic acid and acetic acid, as shown in the equation. Mechanism of basic hydrolysis of ester. This reaction is also known as saponification reaction. The steps of mechanism. As the first step, the hydroxide nucleophiles attack as the electrophilic carbon of the ester, breaking the bond and creating the tetrahedral intermediate. In the second step, the intermediate collapses and reforming of the C double bond O, which is an ester group, and the loose of leaving group, the alkoxide, leading to carboxylic acid. At the third step, an acid-base reaction will occur. Very rapid equilibrium where the alkoxide functions as a base, depolarizing the carboxylic acid. An acidic workup would allow the carboxylic acid to be obtained from the reaction. Acidic hydrolysis of aspirin. The second type of hydrolysis. Aspirin will effect on the acidic media of the stomach, causing activation of gastric acid. So, aspirin will react with acid like HCl in the stomach to produce salicylic acid and acetic acid, as shown in the equation. Mechanism of the acidic hydrolysis of ester. This reaction is also known by Fischer esterification. In the first step of mechanism, an acid-base reaction will occur. Since we only have a weak nucleophile and poor electrophile, so we need to activate the ester. This will occur by protonation of the ester carbonyl, making it more electrophilic. At the second step, the oxygen group of water molecule functions as a nucleophile, attacking the electrophilic carbon in the ester group C double bond O, which the electrons moving toward the oxonium ion, creating tetrahedral intermediate. In the third step, an acid-base reaction will occur by deprotonating the oxygen that came from water molecule to neutralize the charge. In the fourth step, an acid-base reaction will also occur. Need to make the OCH3 leave, but need firstly to convert it to a good leaving group by protonation. In the fifth step, use the electrons of the adjacent oxygen to help push out the leaving group, and also a neutral methanol molecule will produce. In the last step, an acid-base reaction will occur by deprotonation of the oxonium ion, detect the carbonyl of ester group in the carboxylic acid product, and regenerate the acid catalyst.
The preparation of methyl salicylate. Methyl salicylate, or what we call it oil of wintergreen, is an organic ester. When an acid containing the carboxyl group reacts with an alcohol, a compound that containing the hydroxyl group formed an ester. The reaction occurs between the salicylic acid and the alcohol to produce salicylate derivatives like methyl salicylate as shown in the figure below. The mechanism of reaction of a methyl salicylate called the Fischer esterification mechanism, which must include the continuous removal of water from the system and use large excess of alcohol, since the overall reaction is reversible, which is employed to convert carboxylic acid in the presence of alcohol and a strong acid catalyst to give an ester as a final product. For the first step, the carbonyl oxygen is protonated by the acid catalyst, activating it toward a nucleophilic attack from the ethanol. The second step, the alcohol executes a nucleophilic attack on the carbonyl. A lone pair of electrons from the oxygen atom of the alcohol forms a bond with the carbonyl carbon, breaking its pi bond with the other oxygen. The pi bond electrons move up to the oxygen and neutralize its positive charge. The result is an oxonium ion. Third step, now a proton transfer occurs from the oxonium ion to the OH group, giving rise to an activated complex. This can be divided into two further steps, where the alcohol first deprotonated the oxonium ion, giving a tetrahedral intermediate, after which the OH group accepts the proton from the alcohol. The fourth step now occurs the first and second elimination of water, giving a protonated ester. A lone pair of oxygen forms a pi bond with the carbon, thereby expelling the water. For the final step, the remaining positively charged oxygen is deprotonated, giving the required ester as a product. Chemical reaction of methyl salicylate. Now we're talking about hydrolysis of methyl salicylate. This ester will be treated with aqueous base. The hydrolysis reaction that occurs will form methanol, water, and the sodium salt of salicylic acid. Salts of organic compounds usually are soluble in water or will dissolve in water with a bit of heating. Later in the workup, the salt is acidified with acid to convert the organic salt into the protonated carboxylic acid. Therefore, the major organic product of this reaction is salicylic acid as shown in the figure below. Mechanism of reaction. Mechanism of base-catalyzed hydrolysis of esters. Base promotes hydrolysis of esters by providing hydroxide ions, which are strong nucleophiles. First, the hydroxide nucleophiles attacks at the electrophilic carbon of the ester C double bond O, breaking the pi bond and creating the tetrahedral intermediate. Then the intermediate collapses, reforming the C double bond O, resulting in the loss of the leaving group, which is called methoxide, leading to the formation of carboxylic acid. Finally, a very fast exothermic proton transfer drives the reaction to complete. Reaction occurs where the methoxide functions as a base and carries out deprotonation of the carboxylic acid that resulted in formation of الكربوكسيلate, acetate ion, and alcohol الميثانول.
Thank you for watching our overview of salicylates.